In the previous video, we looked at the basics of electricity and useful properties you can get from it like voltage. In this video, we're going to unpack what happens when you connect two ends of a voltage source. Circuits. So if I have a battery here, and I connect the two ends, then we would expect the electrons to move from one end to the other because that would decrease its potential energy. Now we also know that the electrons don't just jump to the other end all at once because, well, batteries don't just burn out the second you connect them, which means that there must be something stopping the electrons from instantly jumping from one end to the other, and that thing is resistance. So resistance really measures the proportionality between the voltage applied and the flow of electrons. But what exactly is the flow of electrons? Well, one way we can measure them is the amount of charge that passes through some area in a certain amount of time. So the change in charge over the change in time. Now we can also define it geometrically. So the charge inside here is equal to the charge per volume times the volume. Seems simple enough. Now we'll rewrite the charge per volume as the charge carrier density, so something like 10 atoms per cubic centimeter, times the charge on each carrier. So maybe the charge on an electron would be the charge on each carrier, and then again multiplied it by the volume. And then we're going to also go ahead and rewrite the volume as the area times the length, where the length is the same thing as the velocity times some change in time. Now why did we go through all this rewriting? Well, it's because now we could just divide both sides by the change in time. And now we'll get that the flow, which is the change in charge over change in time, equals the number of charge carriers, N, times the charge on each of those carriers, Q, times the cross-sectional area of the wire, A, times the velocity of each charge carrier, V. And by the way, this flow is also called current. Another thing we can do is solve for the velocity of the charges in the wire. So let's do that. So we can divide both sides by N, Q, and A to solve for the velocity. And now we'll pick some sensible values and solve for each of these. If you do all the calculations, you get 0.2 millimeters per second.
But how does that make any sense? I mean, if I turn on a light switch, it's almost instant.
Well, that's because you don't have to send a charge through the whole circuit in order to get it going. Instead, it's like a big old conga line, where one charge goes in and one charge goes out. And that process happens almost instantly, which means that the circuit can start and stop almost instantly. And with a good idea of current, we can get back to resistance, because resistance is just how much voltage is required to get a certain amount of current out. So for example, if my resistance is 2, then I need 2 volts to create 1 amp of current. And the equation that we found is usually written like this, and it's called Ohm's law. Voltage is equal to current times resistance. If we can find any 2 of these quantities, then we can solve for the other.
So in practice, if you're going to go build a circuit, you'll get some resistors that look like this. So these are around 200 ohms. This is what a single one looks like. And then you insert them at different parts of the circuit to control the resistance.
So if I'm trying to build a circuit, I can start with a voltage source. This is the symbol for voltage, by the way. And then I'll connect it to resistor R1 and also resistor R2. So if R1 and R2 are different, then what's the current going to look like? So to do that, we can take a look at the geometric definition of a resistor. So remember that in practice, a resistor makes it hard for the electrons to flow through by creating thermal energy. So basically, it's like a constriction in a pipe. So if it's longer, then the electrons are going to have more resistor to go through before they reach the other end, which means that there's going to be more resistance. But if it's wider, then there'll be more paths for the electrons to go through, so they'll flow through more easily. So what we can say is that resistance is proportional to the length of the resistor and inversely proportional to the area of the resistor, or that the resistance is equal to some constant times length divided by area. And if you ever need to get the resistance of some weird object, then you're just going to add it up across each differential length as we've seen before. So when we put 2 resistors in series, one after the other, then we're effectively creating a larger resistor with a larger length. Since the resistance is proportional to length, we can get the effective resistance by just adding R1 and R2. So if our voltage is 9, R1 is 1, and R2 is 2, then the effective resistance is 3, and the current is 3 amps. Another way we can combine the resistors is like this, called in parallel. Now we're effectively increasing the area of the total resistor. Since the resistance is inversely proportional to the area, we add up the inverse of R1 and the inverse of R2, which gives us 1 over R effective. And now we invert both sides, we get the effective resistance. With these 2 methods, you can pretty quickly break down the resistance of a complicated circuit. So like this one right here.
R4 and R5 are in series, one after the other, so we can add them up. R4, 5 and R6 are in parallel, so we can add their inverses. R2 and R3 are also in parallel, so we can add their inverses. And lastly, we can add up the 3 remaining resistances since they're in series. Another useful metric in circuits is the power, or change in energy over change in time.
So if the energy changes by 5 and 5 units a time, then my power is 1.
So we can get power by multiplying current, which is change in charge over change in time, by voltage, which is energy per unit charge. And if you combine it with Ohm's law for an ohmic resistor, you can see that there are 2 other ways to write this. And now we can see why the battery caught on fire, because if the voltage is constant, then the power is inversely proportional to the resistance. So something that doesn't resist current flow that much will get a big spike in energy, and as a result it'll start smoking up. But not all of that current flow is equally distributed. If you have a parallel circuit like this, some of the current will go to the top path, and some will go to the bottom path. And they won't exactly be the same, because more current is going to flow through the lower resistance path. Since charge is conserved, we know that the total current going into both paths must be the same as the total current flowing out of both paths. And since energy is conserved, the change in voltage as you take either path should be the same. Using these 2 equations will usually work for you, but sometimes it's not enough, like in this circuit. And in that case, you're going to want to use the Kirchhoff equations.
Wait.
Kirchhoff.
Oh no, there ain't no way I'm going to be able to pronounce that. So the first Kirchhoff equation says that at a junction, which is where the wires meet, the total charge going in must equal the total charge going out. In other words, current in equals current out because the charge has to go somewhere. The second one tells you that if you start and end in the same place, then you should have the same potential energy. So if you go through a big loop in the circuit, then the voltage gain from the battery minus the voltage drop from each of the resistors, which is equal to I times R, must equal 0.
Now so far, we've been assuming a perfect battery, which means that we get a constant supply of voltage no matter what happens. But in reality, sometimes voltage can fluctuate a little bit, which means it's useful to have a system that can continue to power the circuit during those fluctuations. A capacitor.
Now a capacitor is just a component that's 2 connected metal sheets. And if you put it across a voltage source, then the charges are going to flow to the sheets since they're attracted to the other side. But when they reach the sheets, the same sign charges on the opposite side are repelled, so they basically continue across the circuit, although it's not exactly the same charge. However, now there's more positive charge on one sheet and negative on the other sheet, which means that over time, the capacitor will eventually reach equilibrium when it has a voltage across the plates that's directly opposing the voltage created by the battery. The quantity we use to measure capacitors is the capacitance, C, which is equal to how much charge, Q, you get on the plates when you apply some voltage, V. Now if you want to know exactly how much charge is going to be on the capacitor over time, then we could break it down with a Kirchhoff loop. So remember that means the voltage over a full loop is 0. So the voltage from the battery, V, minus the voltage drop from the capacitor, which we can get from C equals Q over V, voltage is Q over C, and lastly we subtract the voltage drop from the resistor, I times R. Also remember that the current is just the change in charge over change in time. So if you rewrite it like this, we have a differential equation. If we go ahead and solve it, we get this exponential decay or kind of carrying capacity function, which looks like this. So in the beginning, the charge accumulates very quickly, and then it levels off over time as the capacitor is fully charged. And you can also look at the current, which is the slope of the charge curve. In the beginning, a lot of charge is flowing through, and over time it goes to 0 because the capacitor is opposing the voltage from the battery. In a setup where we want the circuit to account for voltage fluctuations, we put them in parallel like this. So when the battery is turned on, at first the current's going to go through the capacitor, charging it up, and then eventually it'll divert to the rest of the circuit. If the voltage source goes out, then the current will continue to flow from the plates of the capacitor. We can go through the same procedure with a Kirchhoff loop equation, and we get the expected result of exponential decay. So it starts off with lots of charge and then quickly gets rid of it through the resistor. That also means that the current is quickly flowing through the capacitor, or really out of the capacitor, into the circuit, and then it levels off over time. Now we could also use the other ideas we've discussed to find the current through the resistor. But in general, you can usually get away with thinking the capacitor is acting like a wire in the beginning when it's charging up its plates, and then over time, it's going to eventually turn into a sort of break in the circuit because it's opposing whatever voltage was applied across it.
But what happens if you put two capacitors together?
So once again, we can look at the geometric definition of a capacitor. We'll call the area of each plate A and the distance between the plates D. Now if you recall from the Gauss's law example from earlier, the electric field of a single plate is the charge density, sigma, over 2 times epsilon naught. So for 2 plates, you're just going to get sigma over epsilon naught. And the charge density is the same thing as charge per area. So we can rewrite this as Q over epsilon naught A. And remember that epsilon naught is just a constant. To get the voltage, we can add up the accumulation of the electric field along some length. This simplifies to just E times the length since the electric field is constant. So in our case, the voltage is Q D over epsilon naught times A. And now remember that the capacitance is just charge divided by voltage. So if we plug in our voltage expression, we'll get that the capacitance is equal to epsilon naught A over D. In other words, it's proportional to the area and inversely proportional to the plate-to-plate distance. So if we have 2 capacitors in parallel, then we effectively have one big capacitor. Since capacitance is proportional to area, the effective capacitance is just the sum of each capacitance on the parallel capacitors. Now if they're in series, we're effectively increasing the plate-to-plate distance. Since distance is proportional to 1 over c, we add the inverses of the capacitances and invert the whole result to get the effective capacitance. So in practice, it's the opposite of resistors. If they're in series, you add their inverses, and if they're in parallel, you just add them up. Now sometimes it's useful to get the energy of a capacitor, and to do that, we can just add up voltage times charge, because those cancel out and we get potential energy. So using the C equals Q over V equation, and plugging in our capacitance, we can get several ways to write the energy. Now if you want to, you can also rewrite the equation 1/2 CV squared like this, and divide both sides by A times D, which is the same thing as the volume. This will get you the energy per volume, or the energy density of the electric field in the capacitor.
Now, a real capacitor doesn't have parallel plates. Instead, they're coiled up into a little cylinder like this. And in between the plates, they don't just have air. Instead, there's an insulating material, which is one that doesn't conduct electricity.
To see why, let's take a look at what happens to the insulator when you insert it. While it can't conduct charges, the atoms can reorient themselves, which means they'll take this configuration since the opposites attract. On the inside of the material, the pluses and the minuses cancel, but on the outside, you get a small electric field pointing like this, opposite the electric field from the capacitor. Since the voltage is derived from the electric field, a weaker electric field means less voltage. So now we have the same amount of charge on each plate for less voltage, which means our capacitor is more effective. So basically the insulator, also called the dielectric, weakens the electric field by some factor kappa. And one way you can think of this is that it changes the permittivity constant from epsilon naught to kappa times epsilon naught.
So I got a circuit right here. It's got some capacitors, resistor, there's a light bulb right here. And the outlet is actually just a voltage source. So if I go ahead and I plug this in.
Okay, so it turns out that the voltage in your wall uses alternating current. So instead of the voltage looking like this, it looks like this. So for some general AC circuit, it's going to look like a normal sine wave, scaled up by a factor V0, sped up by the angular frequency, omega, and shifted by a constant delta. And in our case, we're just going to ignore the delta because it's going to make the math a little bit easier. V equals IR still applies here. So if you've got a resistor, then you can find the current pretty easily. It's going to line up with the voltage. Wall outlets are usually like 100 to 300 volts, but they kind of vary around the world. And you can already see there's a problem here. How do I go from this wiggly sine graph to a constant number like 100? We can't just take the average of the graph because all sine waves have an average of 0. So instead, what we have to do is square the wave, then take the average, then take the square root of that average. And this is called the root mean square, or RMS, and it's usually the quantity people are referring to in AC circuits. So when you see that the wall voltage is around 100 to 300 volts, that means that the root mean square voltage is 100 to 300 volts. Ohm's law and the power equation are going to work just fine if you use the root mean square quantities of everything. But what if I have a capacitor? Well, in a low frequency situation, the capacitor is going to get to charge up, so it's going to oppose the current flow a lot of the time. But in a high frequency situation, it's not going to have enough time to fully charge up, so it's going to let more current through as the AC circuit's running. So the opposition to the AC current is inversely proportional to the frequency. And also, the better capacitor you have, the more it's going to charge up, right? Because it can get more charge per voltage as the voltage increases and decreases. So the better a capacitor you have, the more it's going to be charging up and discharging over time, which means that it's not going to be opposing the voltage as much in an AC circuit. You can work this out from the definition of capacitance in the sine wave, or you could just look at the proportionalities and kind of think about it. But in both cases, you get that the proportionality between current and voltage is this quantity 1 over omega c. It's like resistance, but it depends on how quickly the circuit's changing, and we call it reactance. And the symbol we use for reactance is X. So if you have a smaller capacitor or a more slowly changing circuit, then there won't be as much max current when you apply some max voltage. And because of these relations, the current on a capacitor is always going to lead the voltage source by 90 degrees, if you look at the sine waves. To see why, let's walk through what's happening here. When we first turn on the voltage, the capacitor acts like a wire, so it very quickly starts running current and accumulating charge. Then, the voltage starts to level off, and the current starts to level off too. The maximum charge stored on the capacitor occurs right here when you have maximum voltage. And you can see this since the charge is the area under the current curve. So right before the current goes negative, it's going to have the maximum charge. Now when you start decreasing the voltage, the capacitor has excess charge on it. So to get rid of it, it's going to start discharging by sending current in the opposite direction, which is where we get the negative current from. And it'll keep discharging more and more until the voltage reaches 0. At this point, the areas under the curves cancel, which means that there's no charge on the capacitor right now. So when the voltage starts going negative, it's going to act like a wire again, quickly drawing lots of current, except now it's in the opposite direction. And now we have the same cycle repeating, but for negative charge and negative current. A different way to imagine this is to show the sine waves as spinning vectors like this, where the vertical axis represents the voltage across the circuit. So the voltage might look like this. Our maximum voltage is V0, since that's the value when the wave hits the top. And omega t is the angle under the vector right here, and represents how far along the wave we are. So it starts at 0, and then increases as we go along the path. And the height is the voltage, V0 sine of omega t, because the sine is the opposite over hypotenuse. The opposite is the voltage here, and the hypotenuse is the maximum voltage V0. Now the capacitor, as we said before, will be 90 degrees ahead. So we could show it vertically like this. Now if you have a capacitor and a resistor in the same circuit, we know that the resistor will follow the voltage, and we also know that resistors in series add. So we can get the total resistance, in this case called the impedance, since it also relies on the frequency, by adding the resistance and the reactance vectors. The magnitude of the impedance is equal to the length of the vectors added together, and since they're always perpendicular, it's the same as the length of the hypotenuse of this right triangle. Z equals square root of x squared plus r squared, where z is the symbol we use for impedance. So basically impedance measures how much current you get when you apply a certain amount of voltage, but in AC circuits, the frequency also matters, which is why it's a different quantity than resistance. And now that you know about AC circuits, you can connect stuff into a wall and you'll be okay. Probably. Maybe. In the next video, we're going to talk about magnetism. I'll see you there.